With that, please join me in welcoming our next speaker, Adam Klivans. He will get ready. He's an associate professor in computer science at University of Texas in Austin. We're glad to have him here and read his bio in your program. And with that, Adam, it's all yours.
Thanks to the organizers for inviting me to come give a talk. I'm a computer science professor at UT up in Austin. And just to say a few words about the type of work that I do, I work in foundations of machine learning. So the core questions in my field are, what sort of algorithms can we come up with, learning algorithms, machine learning algorithms, and can we prove rigorously that our algorithms are going to both run fast and use few samples. Okay, and so both of those things are super important in pretty much any machine learning system that you'd like to deploy. And foundations of machine learning has been a very impactful field. If you've ever used a boosting algorithm or a support vector machine, those are the results of research in foundations of machine learning. And so the real hope is to come up with a really broad class of interesting, expressive algorithms that we can say things, rigorously and provably about. And even today, for any of you that sort of do deep learning or learn neural networks, you'll know that at the core of all of these, complicated machine learning systems are really shockingly simple algorithms like gradient descent. Okay, so the possibilities of coming up with new, powerful, interesting, expressive algorithms are really exciting because it's sort of amazing how far we've gotten with the simple algorithms that we do have. So what I want to tell you about, I guess I should, let me keep track of time here, but what I want to tell you about is an algorithm that I recently came up with my colleague Raghu Mekka at UCLA. And the problem that we're studying is something about learning Markov random fields. And if there's too much jargon for you already, it's really not that complicated. I'll explain it to you. So what I'd like to do is just explain the problem to you. It's sort of a natural and well-studied problem. The algorithm itself is also actually quite simple. And I probably won't have time to prove to you that it works, but it does. And I'll tell you the bounds that we get. Okay? So this is a talk about unsupervised learning, if you're familiar with supervised or unsupervised learning. In unsupervised learning, there's just some distribution, which I've called D. I hope you can read my handwriting, but there's some distribution D. It could be arbitrary. And let's say the distribution is on bit strings of length n. Okay, so I've written -1, 1 to the n. It could also be 0, 1 to the n. Doesn't matter. So you take a draw from this distribution, and unbeknownst to you, there is some graph that you don't know. Okay? There's a graph that's unknown to you, and it's often referred to as a dependency graph. Okay, and the graph has the following interesting property. For two vertices, so there are n vertices in this graph because you're looking at strings of length n, and two vertices I and j do not have an edge between them, do not have an edge between them, if they're independent, conditioned on any setting of i's neighbors in the graph. Okay? This is an undirected graphical model, if you're familiar with graphical models. For those of you who aren't, you can kind of see that this graph encodes some pretty fundamental information about the distribution. If you could view these strings of length n as strings of features, so we have n features, and as you can imagine, taking a data set and figuring out what features are sort of conditionally independent from other features is really fundamental and important. Okay, so here we have this distribution, and that's really what we want to know. We want to understand what are the independence properties of the features in this distribution. And there's some graph encoding that information, and it's unknown to us. All that we, the learner, have access to are independent draws from this distribution. Okay? So there are two types of graphical models. I apologize for the math. There are two types of graphical models that I'll be talking about. The first They're both very famous. The first one is called the icing model. And what that says is, hey, not only is there this underlying graph that encodes these conditional dependencies, but the PDF, the probability distribution itself, is just a function of the edge weights of that graph. Okay, so the probability that x receives is proportional to x, that means e to the minus, and then a sum over all edges in this graph of some weight, wi, wj, times xi, xj. Remember, the xi's are your features. Then there's this plus sum I theta I xi that's called the mean field. And then in order to make this a distribution, you have to multiply by a normalization factor 1 over z. Okay? So in the icing model, you have both this unknown graph, and you have this really nice form of the PDF. And then there's something called a T-wise, or an order T Markov random field, which I've written TMRF. And this basically says, hey, there's an underlying graph that you don't know for this distribution. And the PDF can be written as the sum over all cliques in the graph of size t of some weight given to that clique times some product of variables involved in that clique. And there's a really cool theorem that basically says, if you give me a distribution, then it can be written as a PDF for some sufficiently large value t of this form. Okay, so if the TMRF is annoying to you, just think about the icing model. Really, that's all I'm sort of going to talk about. I mean, that's mainly what I'm going to talk about. Okay? So the idea is you have this graph. There are these edge weights. You don't know them. And there's a PDF that you also don't know. And the PDF has some really simple, is really some simple function of the edge weights. Everybody, any questions about that? No? Perfectly clear. OK. OK, so just to recap, you're given draws from this distribution from some TMRF, or just some icing model. OK? And you're trying to figure out, hey, what are the edges of this graph? OK? This is called structure learning for MRFs. It has many applications. For example, there are many applications in computational biology for modeling protein-protein interactions, in natural language. I mean, these undirected graphical models are in some sense really a workhorse family of probabilistic models in machine learning, computer science, statistics. Just nod if you've heard of a graphical model. Let me see how many people know what a graphical model is. Yeah, I see a lot of nodding. OK, good. OK, and there's been a lot of work on algorithms for trying to figure out the structure of these graphs. OK, so when my co-author told me that this problem was still open, I was sort of shocked and happy to solve it. And yeah, so what I want to do is tell you an algorithm for reconstructing these graphs. And the nice thing about this algorithm is that it's going to be optimal in every sense. It will have essentially the optimal running time, and it will use the fewest number of examples that you could provably get away with. And it's also a simple algorithm. Okay. Okay. So just a few. I just want to say something about non-degeneracy. So let's assume that we have some underlying graph G. Its degree. So every vertex has, let's say, d edges coming out of it. Okay? This is the standard scenario that you're looking at. And we're going to have to assume that each edge weight is lower bounded by some small quantity alpha. Okay? Because if you don't lower bound it by this is a standard thing to do. If you don't lower bound it by some quantity, if it's super, super, super small, then it's impossible to tell whether or not that edge is there. Like if it's too exponentially small, you have no hope of determining whether the edge is there or not. And then there's always the brute force search algorithm in this scenario, which says, OK, I have a vertex v, and I want to figure out its neighborhood in this graph. So one way I could do that is I could just look at all neighborhoods of size d and take some statistics and see which neighborhood sort of matches up best with this vertex. And that runs in time n to the d. Okay, so that's what you should be thinking of as sort of the brute force algorithm. This is a classical known old result. And so that's we want to do something smarter than that. Okay, so here's the, are you ready for the algorithm? Here's the algorithm. Okay. Oh yeah, okay, sorry. There's one last thing I have to tell you. I just want to remind you what the sigmoid function is. Okay, it's this, if you do any deep learning, you're probably familiar with it. It's just a function. I've tried to draw it there, and it has that form. It's 1 over 1, sigma of z is 1 over 1 plus e to the minus z. So it goes to 0 this way, and it goes to 1 this way, and it has that nice curve shape. Okay, that's the one thing I need. Okay, so here's the algorithm. It's all in this one slide. So what I'm going to do intuitively, you can ignore the slide if you'd like, intuitively is I'm going to take a draw from this distribution. And I want to figure out who are the neighbors of I, vertex I. Okay? So I'm going to cover up the ith feature of this draw that I took from the distribution. I'm just going to cover it up. I'm trying to figure out who the neighbors of I are. I'm going to, it's some bit. I'm going to just cover it up. And then I'm going to view all the other bits in that string as votes for whether they think what I've covered up is 1 or minus 1. Okay, so I could take a string, x1, x2, x3, dot, 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 xi. I cover up xi. I look at everybody else's bit, and I view them as votes for what they think, even though they're just different features. I'm going to interpret them as votes for what this bit is. Okay? And every feature that matches this, so I'm going to remove my hand. Every feature that agrees with this bit, I'm going to say basically like, nice job, you predicted correctly. And every feature that disagrees with this bit, I'm going to say, oh, you were wrong. Okay? And features that were wrong are going to be penalized. How am I going to penalize those features? I'm going to multiply them by some value less than 1. And features that are correct, they sort of won't get penalized at all. Okay, so I take a string, I cover up the ith bit, I look at everybody else. Everybody who's wrong about predicting this bit gets multiplied by some factor, and everybody who's right is sort of left alone. I do that many times, okay, essentially, and the weights that I end up with converge to the weights in the neighborhood of vertex I. And sort of interestingly, they converge at an optimal rate. Okay, so what I've written in this slide is, for every vertex I, you get 2 neighbors, j plus and j minus. And this is because intuitively, I don't know if vertex j is positively correlated with you or negatively correlated with you. So you get 2 neighbors, and they get 2 weights, wj plus and wj minus. Then I draw z1 through zn. zj is its vote for zi. And then the negation of zj is the vote is j minus's vote for zi. Obviously, it's going to be the opposite vote. And then I compute some prediction, p, which is just a weighted vote of all of these features. Now, the only thing I haven't told you is, how do I, so p is literally a weighted average of all the votes of all the other features for what they think i's bit is. And the only thing I haven't told you is, how do you actually update these weights? How do you do the penalty? Okay. So here's how you do the penalty. This is sort of the mathiest slide I have in the whole talk. Here's how you do the penalty. You multiply xi. You form this value lj, and it's the sigmoid of the prediction minus 1 minus zi over 2. That's xi's guess moved to 0, 1, times zj divided by 2. And then I multiply wj. I take its old weight, and I multiply it by beta raised to the lj. Okay, so for those of you who want, I put this up here just in case you really want to see concretely the entire algorithm. This is the penalty factor that you use to multiply all the other weights by. Okay, it's some simple function that involves a sigmoid. And you can take my word for it that features that predict incorrectly get penalized more than features that predict correctly. OK, so then the next question is, well, how many draws do I need until these edge weights that I keep remultiplying by different factors, how many draws do I need until the estimate that I get for that edge weight is within epsilon of its true value? And it turns out the answer is 2 raised to the order d times log of n over epsilon times 1 over epsilon to the 4th. OK? And remember, we were trying to beat n to the d. OK, so the difference between 2 to the d and n to the d, it's pretty large. The other nice thing is that the running time of this algorithm is n squared times the number of samples. And that's because first I need to figure out the first I need to figure out the neighborhood of vertex 1. So I have to take all these draws and look at all its neighbors. Then I have to figure out the neighborhood of vertex 2. I have to take all these draws. So I have to figure out the neighborhoods of n vertices. Doing that takes time n, and so I end up with time n squared. So I get 2 to the d log n over epsilon n squared times the number of samples. The other nice thing about this algorithm is that you can have a graph that has a very large degree, doesn't have to have bounded degree. But as long as the sum of the edge weights in every neighborhood is bounded, then this analysis will still work. And you'll still, instead of a d here, you'll replace it with sum of the edge weights. Not only does it recover that graph that I talked about on the first slide, it actually tells you what the edge weights are. So the traditional problems of structure learning for an undirected graphical model are just tell me if there's an edge there or not. This will actually tell you what the edge weight is, and in that sense, you can actually recover the PDF for the underlying Ising model. Furthermore, you can extend this to the non-binary case. So if you have, instead of +1 - 1 to the n, you have a larger alphabet, it will still work. And one of the main points of doing this is that it will extend to higher order Markov random fields. So order t, those order t MRFs that I talked about earlier, this algorithm will still apply to. The reason why I say it's optimal is that there's actually a lower bound known in statistics that you need roughly 2 to the, ignore the beta for a moment, but you need roughly 2 to the d times log n samples divided by some other factor on alpha. So it's almost optimal. And the best you could really hope for in terms of running time for this problem is n to the 1.62. This is an interesting reduction from a problem called the light bulb problem. So it's possible that you could improve it from n squared to n to the 1.62. But it's pretty close. Again, sort of almost optimal. And the reason why this problem was, I didn't realize this, I thought this problem had been solved, but it turns out that all prior work for learning these types of graphs, when you're given a set of examples, required some pretty strong assumptions on the graph itself. There's an assumption called correlation decay. And that means that if you have 2 features in your graph that are far apart, or that as vertices in your graph, as they get farther apart in your graph, they become more and more independent. So under that assumption, yes, you can come up with some algorithms, although it's sort of controversial as to when that assumption holds or not. Then there are known incoherence assumptions. So if you've ever done any compressed sensing, you're familiar with the notion of incoherence. If their examples are incoherent, there are also algorithms known for reconstructing these graphs. And one thing that's nice about our algorithm is that it doesn't require any assumptions. What it really builds on is this beautiful paper due to Guy Bressler from a couple of years ago. He gave an algorithm, really nice result because it didn't require any assumptions, but its dependence was 2 to the 2 to the d times log n. And as you recall, what we were able to get was 2 to the d. And there's also a paper due to Vuffray et al. That did get sort of the right dependence on the sample complexity for a large class of Markov random fields, or a large class of Ising models, I should say, and ran in time n to the 4th. Now, what prior work was there for higher order MRFs when t is larger than 2? As far as we could tell, nothing. And so our result, if instead of an icing model, you want to use a higher order, an order t MRF, will require 2 to the d to the t log n examples and run in time n to the t. There was also some independent work that appeared at NIPS this year that got 2 to the 2 to the d to the t. So we're still exponentially better than that one. This n to the t running time is also essentially inherent if you assume that certain problems that have been studied for years in computational learning theory are really hard. OK, so why does our algorithm work? I'll just say sort of one thing about our algorithm, because first of all, it sort of has a cool name. It's called sparsitron. And what it does is the following. So if you're familiar with the notion, so what it does is some sort of regression. It solves some sort of regression problem. So imagine that we're given draws from a distribution, x1, y1, x2, y2, and so on and so forth. And I know that the conditional mean of y given x is equal to a sigmoid, remember that sigmoid function, of some hidden vector v inner product x. Okay? Now, if the conditional mean function were a linear function, then this would precisely be the setup of just plain old linear regression. And you could run ordinary least squares to solve this problem, if the conditional mean were a linear function. Okay? Conditional mean is not a linear function in this particular setup. It's a sigmoid of a linear function, which is sometimes referred to as a generalized linear model. Okay, so we're doing something sort of more difficult and more general than linear regression. We're solving these sigmoidal linear regression problems. And what we do is, if you're given this guarantee that your data is generated this way, our algorithm, sparsitron, will actually output a weight vector w that's very close to v. It's very close to the hidden weight vector that you were looking for. So in particular, its squared loss will be within epsilon of what the true conditional mean function is. And the other nice thing about our algorithm is that the sample complexity is sort of the 1 norm of v squared times log n divided by epsilon squared. And it works for all distributions. OK? The algorithm really relies on this, what I call fundamental result in the best experts literature, or the weighted majority literature. It's a famous result due to Freund and Shapiri. They use something called hedge, where you have a bunch of experts, and you need to use some averaging strategy on your experts in order to predict as well as the best one. And you can kind of see that happening in the algorithm that I described earlier, where I have these features, and I'm going to form these predictions of these features. And this sort of comes into play in the analysis to prove that the rate of convergence is optimal. So I'll basically jump, since I only have 1 or 2 minutes left, let me tell you that some interesting open problems. First is to improve the dependence on 1 over epsilon. Second would be our algorithm works for all discrete alphabets, but the case when the alphabet is Gaussian is open. Gaussian graphical models are actually open. It's a super intriguing problem, and it strangely has sort of nothing to do with the problems that we solved here. And there's also, that sigmoid function. It's not a coincidence that the sigmoid appears here. There is a relationship to learning neural networks, and I'll just give an advertisement for an upcoming work that I have. So this algorithm was sparsitron. I have a new algorithm coming out called alphatron. And if you're interested in learning neural networks, alphatron does some pretty interesting things. It's joint work with my student, Serbi Goel. Okay, so I'll just end here. Thank you.
Thank you. Is there any quick question? I think we have room for one question. OK, Moshe.
Do you know how well the algorithm behaves in practice?
We're working on that right now. It's really new work. I'm just giving a talk on it at Fox in a couple weeks. So I have some students working on it, but it works in the sense we did it on some synthetic data, and it converges quickly and works on synthetic data. But that's just the first step.
Join me. Thanking our speaker again. And